Hello, everyone. Welcome to this open neuromorphic talk. I'm very pleased to have today with us Maxence from Rain AI. Gonna bring him up right here. Hey, Maxence. Nice to see
So,
you. How are
hi,
you doing?
Gregor.
All good?
Yeah, good. Thanks a lot for inviting me.
No, it's my pleasure. It's really cool to have you. Where are you located at the moment?
Right now, I'm based in Paris, and I'm working remotely for Rain, which is based in San Francisco. Like most of us, like few of us are actually based in San Francisco. We are all spread across the US and Europe. We are 3 employees in Europe and 33 in the US.
Oh, really nice. That's cool. So you're working with West Coast quite a bit, then you're working late nights.
No. Actually, I'm sticking to my own time zone. So we have 3 hours time overlap per day, and which is enough, to accommodate
Nice.
requests. So it's okay.
Cool. May I ask you to introduce yourself a bit? Maybe you can talk a bit about your background and how you end up doing what you're doing.
Yeah, sure. So I have a typical engineering background as a former French student. So I graduated from a École Polytechnique, and I studied theoretical physics and applied mathematics. And I actually stumbled upon neuromorphic computing when looking for a PhD topic at the intersection of physics and AI. And so I did my PhD with Damien Kerlioz and Julie Crollier. And then I actually had the chance to meet with Benjamin Sellier during my PhD, which led me to collaborate with, among others, Joshua Bengio and Blake Richard. So it actually led me to at the intersection between neuroscience and artificial intelligence. And actually, after I completed my PhD, I pursued a little bit this neuro AI research with Joshua, actually also remotely because it was during the COVID pandemic, and then actually paused neuromorphic research for about a year and a half when working at IBM Research in Paris. So I was working on AI safety, namely uncertainty quantification and interpretable AI systems. And then when Rain raised its a Series A round, $25 million, I actually emailed them saying, "Hey, would you be interested if I applied?" And then I joined Rain remotely since 2022 as a researcher, as a research scientist. And so I've been at Rain for a year and a half right now.
Really cool. It's really cool. So today, I mean, we're gonna hear about what I feel like is more like a pragmatic approach to like well, bio-inspired computing, if I may say so at all. So where was that? Where did that come from? Like, why are you not a neuromorphic researcher? Like, where does this pragmatism come from?
Actually, I intended to finish my presentation by my stance on neuromorphic computing. But if you ask me a question, I'm happy to elaborate quickly. But perhaps in a nutshell, I think that this neuroscience inspiration in so-called neuromorphic computing is a little bit overhyped, and I think a lot of people fool themselves into mimicking the brain for the sake of mimicking the brain rather than using it as a means to achieve better energy efficiency. And so I think that we need to tackle be pragmatic in the sense that we need first to prove energy efficient approaches at scale, and second, really focusing on exactly what are the leverages to reduce this energy consumption, which is what I'm going to talk about today.
Nice, really cool. Well, with that, I think I'm gonna leave the stage to you, and I will keep questions that are being asked on the chat until the end of the presentation, so that we can have a more like open discussion afterwards. If that's right for you. Cool. All right, let's do that and take it away, Maxence. Thank you.
So, hi everybody, and thanks for attending this presentation. So, I will be talking about how at Rain we envision the acceleration of inference and training at the edge. Okay, so I cannot go to the next slide. Oh yeah, there we go. Okay, oops. Okay, so what is our goal? So our goal is not to build an artificial brain, contrary to the the original narrative of RAIN at its very beginning in 2017. I would rather say that it's about building AI accelerators for inference and training running at the edge. So yeah, actually, I would say that the way we differentiate ourselves from our competitors is by our focus on the edge market rather than the cloud market. I don't think we are to compete with NVIDIA in the short run, and also on training, because there are lots of companies tackling the design of inference engines, but a few of them are actually tackling training at the edge. Namely, instead of deploying a frozen architecture on the chip and then it doesn't change at all forever, then you want your neural network to be able to change on the fly with a new incoming data. So we are a Series A startup with 36 employees. As I said, we have our office in San Francisco in the Mission District, and we are almost all working remotely from all around the globe, in US, in France, and in the UK as well, and Switzerland also, I forgot to mention. And so yeah, I want to insist on this because so if you are ever interested to join RAIN, you can actually work from anywhere. So that's clearly an advantage. So okay, our vision is the following, and you will probably not learn much about this, already things that you know, but our vision is that AI is costly because of data movement, compute, and because of the gap between software and circuits. So I'm going to break this down further. So I'm going to talk about data movement. So you probably know very well this picture. So actually, what is depicted here on the right, top right, is a chip with it's a cartoon of a chip with a hierarchy of memory, namely the DRAM memory, global buffer. Also, the processing. You can see the processing elements and the arithmetic logic unit with some local registers. And so here, what we evaluate below is the cost of accessing data from different level of this memory hierarchy, namely from the register file, from the processing element, from the buffer, from the DRAM. So the energy consumption needed to access this data at these different levels compared to the operation itself. So here, what we consider is a MAC operation. And so what you can see is that it's at most 200 times more expensive to access data than compute with it. And so that's what calls for in-memory computing. Actually, it's hidden behind me. Yeah, thank you, Greg. So yeah, this actually calls for in-memory computing. This idea that you want to have compute in the middle of embedded in memory. Okay, or at least to bring memory and as close as possible to compute, which would be near compute memory. So, sorry, near memory compute. Okay, so AI is costly not only because of data movement, but also because of compute, of course. So, and compute, so here, what we mean by compute is performing those vector matrix multiplication, or perhaps sometimes matrix multiplication. And so how do we go about reducing the cost of this operation? So if you can reduce the cost of those operations, then you can actually significantly speed up training and inference. So in the short run, most obvious answer is that you can accelerate compute by quantizing as much as you can, your weights, your activations. And in the long run, the way you can actually reduce the cost of compute is to use analog in-memory computing, namely instead of doing, you leverage the laws of physics, Kirchhoff law of currents, to perform vector matrix multiplication. So I would say that it spans two different time horizons, a short run horizon and a long run horizon. And of course, in between, you have hybrid solutions between digital and analog. And also, lastly, AI is costly because of the gap between software and circuits. So in fact, when you write the code in Python and you import your PyTorch library, you have lots of abstractions between the instructions that you have in your code and the way it's being executed on the circuit. And in fact, all the algorithms that you are using, be it the algorithm that depicts the model behavior itself, or backpropagation, or any algorithm that you do at the instruction level, is totally agnostic to how it's actually performed on the hardware. And in fact, it's also for ease of use. You don't want to be aware exactly of what happens. And that's the very point of using a high-level language, is not to be aware of what happens at the physical level. But it entails a cost, which is that you have many layers of abstractions in between your instructions and between your circuits. Namely, your instruction is being compiled to machine language, and then it's further converted to instruction level architecture, and then down to your chip architecture, and then finally your instruction is executed out of the in your circuits. And so one of the ways we actually tackle this problem at Brain is by bringing circuits and algorithms as close as possible. And instead of having physics agnostic algorithms at the top of all of these layers of abstraction, we rather want to have physics-driven algorithm, where there's no longer a distinction between an abstract mathematical model and the circuit. The model becomes the circuit itself. And the learning algorithms is performed out of the model dynamics. So I would say this is something that is specific to RAIN. We are deeply convinced about the relevance of this both engineering and theoretical effort. Okay, so what is our roadmap? So right now we focus on digital in-memory computing, plus we optimize everything end-to-end across the whole hardware and software stack. Namely, we developed our own custom quantization algorithms, also our own learning algorithms, and so on. Without reinventing the wheel, standard models. We build our own custom compiler, our own custom machine instructions, custom chip architecture, custom digital SRAM IMC core. And so, I would say in the short run, we do painstaking engineering. And in the long run, we want to move towards analog in-memory computing, along with those physics-driven algorithms, as I mentioned before. And so this actually, I would say this describes how we separate engineering and research at RAIN. I would say, engineering is everything that pertains to the design of our product and, digital in-memory computing. And research pertains to what we do in the long run, analog in-memory computing, physics-driven learning algorithms, and also what there is in between also. There is an applied research team at RAIN that bridges efforts between research and engineering. So if you have questions about this, I'm happy to later. I'm happy to answer. Okay, so I'm going to focus a little bit on what I mean by our custom chip architecture and custom digital SRAM IMC core, and perhaps give an overview of the guiding principles for the design of these two. So we are currently developing a fully custom SRAM-based quantized in-memory computing block. And so I want to clarify exactly what I mean by in-memory computing, precisely. So here, okay, you can see an SRAM cell with actually 6 transistors. And the idea here is to, and yeah, also you have a digital circuit that performs bitwise multiplication between a bit of weight and a bit of activation. And so what I want to show you here is that this SRAM cell both sustain the storage of the weight and this bitwise multiplication between 1 bit of weight and 1 bit of activation. So, and here the idea is that to perform this operation, this WB times in B, as you can see on this cartoon, you don't need to fetch for the data because it's already there. It's already built into your SRAM cell, right? So namely this operation, this bitwise multiplication, is performed at the very place where the weight is stored. Hence, this name in-memory computing. Then if we zoom out a little bit, how we would implement vector matrix multiplication is by assembling many such SRAM bit cells and then use an adder tree to obtain the final result of the vector matrix multiplication. So I want to insist here that this is standard digital circuitry, and there's nothing analog here. I'm emphasizing this because we tackled the analog. We wanted to tackle analog computing at the very beginning of RAIN, but we've completely shifted to a digital computing in the short run. And so, okay, so this is our IMC block. So namely SRAM bit cells, and then other trees, and then you can actually perform your vector matrix multiplication this way. And then once you have, so an IMC block actually defines what we call the compute engine. And once you have a compute engine, and if you zoom out a little bit more, then of course, we are not able necessarily to map a single vector matrix multiplication into a single compute engine. So we need to somehow split vector matrix multiplication into several compute engines. And so these need to communicate in a certain fashion. And so this is what is actually depicted on the right. You can see that so here it's, okay, we first add our compute engines, and if we zoom out, we are at the level of the compute tile, what we call a compute tile. And the compute tile is an assembly of several compute engines. And you can see those compute engines in yellow. You can see buses in between compute engines in purple. And so we may also have another memory level here, so which is depicted as a buffer, as well as a RISC-V, because we may need to have dedicated processor to perform digital operations, like namely, for example, what pertains to using activation functions, softmax operation, or sigmoid. So yeah, activation functions and things that cannot be natively implemented in the compute engine, essentially. And so on and so forth. We could zoom out even more on this architecture, but this is actually the main principle guiding the design of our chip. So here so just to give you a hint of the projected performance of our chip. So here I'm taking as a benchmark SIMD vector processing unit, which is a standard benchmark for acceleration. And then on the right, I illustrate this same numbers, but with the projection of our chip, which is going to be built by the end of the year. And so you can see that we have almost an order of magnitude more power intense. An order of magnitude more Mach per nanosecond, although we are using a slower clock, namely a smaller clock frequency, and also much smaller energy consumption. And this is due to how we designed the architecture, and namely in memory computing. Okay, now tackling the highest level of this end-to-end optimization, namely, how we what are the numerics that we use for our chip. So yeah, as you know, we need somehow to represent our data, and as I told you, the main principle main leverage to reduce energy consumption for computation is to actually compress weights and activations. So here, what I depict is the vector matrix multiplication, namely, you can imagine matrix depicting a weight and a column vector depicting an input activation. And so what we would do typically is to represent, so we quantize the weights and the activations into an exponent part and an integer part, where the integer part is actually represented with an integer 8, and the scale bar is represented, say, in brain float 16. But we could also use other representation for the exponent, namely floating point as well. And so our compute engine actually operates with integer primitives, which means that we take the integer part of the matrix, integer part of the vector to be multiplied by this matrix, and this is actually what we do in our compute engine. So we manipulate integer primitives, and then we would store the output of this vector matrix multiplication in integer 16. And then to obtain the resulting dequantized output, we will multiply the scales together and multiply them by the output of the compute engine, and then compress them back into brain float 16. So you see here, so nothing very new. It's a really, really standard thing. And so yeah, that's what I was saying before. Our IMC core operates with integer primitives. Also, yeah, so we actually optimize training in the same way as we optimize inference, namely by quantizing gradients. So this is what I call quantized training. And so quantized training actually yields other subtasks, namely test time adaptation, continual learning, and federated learning. So why are we interested about those fields? Test time adaptation, because you may pre-train your model off chip on given data distribution, and then once you deploy it onto your chip, the edge on your phone, then the data you feed your chip with might be different from the one that was seen during training. So namely, there's a shift in the training compared to the training distribution. So you might need your model to be able to adapt on the fly to distribution that is different from the one that was seen during training. So this is called test time adaptation. And so you may have constraints, because while you may have labels during training of your chip to come up with your initial model, at test time you may not have such labels. So or you may no longer have at your disposal training samples. So how do you adapt to data on the fly? Continual learning. So the reason why we are interested about this is that when we learn at the edge, we may forget about what we learned previously. So how do we balance this trade-off between learning new stuff without forgetting too much about what we learned previously? And federated learning is because we may not have enough data of our own, typically in a cross-device setting where there's a server and there are several clients, namely those clients being, for example, mobile phones. And it could be that we want to learn a model at the edge, and for which we don't generate sufficient amount of data. So you might want to leverage the other clients' data without explicitly accessing other clients' data. So how can you do this in a distributed setting? Then this calls for federated learning. So I would say that on-device learning naturally fits into this federated learning setting, especially the cross-device federated learning setting where clients have limited memory budget and compute. And so these are the topics we are essentially tackling with respect to training. So right now our focus is on small vision models. So you might be a little bit disappointed we are not yet tackling large language models. So typically these are the models we are looking at: ResNet architectures, YOLA architectures, light Ethernet architecture, and so on. And so we are considering essentially image tasks, namely image recognition, semantic segmentation, pose estimation, and so on. I insist on this. We focus on something that is a little bit restricted for now, and so our first chips will be highly customized for standard vision models, but not for attention models. And so now I'd be talking about a little bit about this piece, which is of high interest to me because it pertains to research. So what I told you is that we want to reduce as much as possible this abstraction between the model, namely, say, for example, a fit-forward model that you declare in your Python script, and the circuit itself that sustains computations that are needed to, say, execute a forward pass. So here in this vision, the circuit is the model itself. So namely here you have a circuit where some input is encoded as an input voltage, which is here, for instance, Vin, and the parameters of your model are encoded as weights, nonlinearities as diodes, and then you need to pick one pair of nodes to encode for the output of your model. For example, Vout could encode for the output of your model. So then, once you have physically encoded your input and your output, the idea is that you want to adjust the weights, namely the value of the consequences of your model, to reduce some given loss. And so then the question is, how can this circuit compute a loss gradient by itself? So can this circuit alone learn somehow by itself? So there are several difficulties here, because if you think about it, circuits are implicit models. They are not exactly fit-forward models. What I mean by implicit is that Vout, you cannot necessarily write Vout as an explicit function of Vin, mathematically speaking. Rather, Vout and Vin satisfy a set of physical laws, namely Kirchhoff laws for voltage, for currents. You have the diode, and also we we have to satisfy we have to abide by the constraints imposed by the diode. So we may not be able to solve analytically for V out as an explicit function of Vane. So this falls in the realm of implicit models. And also, gradient computation generally happens on a separate circuit, because we typically solve for the error signal of the circuit through the adjoint of the circuit, which is not necessarily called, it matches the original circuit. And on our first chip at Rain, for example, you would use different tiles for the forward pass and other tiles for the backward pass, because generally speaking, you need to, unless you introduce further assumptions on your model, you need to separate these two pathways. And this is referred to in the biological literature as also as the weight transport, which is that if you have two different circuits, one to perform the forward pass, the other one to perform the backward pass, then you need to transport information across these two circuits. And so this is the case, except for energy-based models. For energy-based models, you can use the same model for both the forward pass and backward pass, because these models are self-adjoint. And so actually this has motivated a long line of research. So I'm just including a few of these papers here. And so, yeah, I don't know if I can say a little bit about this, but it was actually demonstrated in 2020 with a proof of concept that we can use analog circuits so that we can come up with energy-based analog circuits so that we can apply equilibrium propagation to these circuits to compute gradients in situ, so using the same circuit. And this was actually experimentally demonstrated a little bit later, 2 years later, by Yi et al. And more recently, we're still working on actually algorithmic advances to come up with clear prescriptions as to which energy-based model to use on circuits, because there are lots of heuristics in the literature, and so we are still working a lot on algorithms as well. And so I can give a little bit. I can give some hints about our ongoing research. So yeah, first, we look beyond the first-order optimization, namely how can we leverage circuit physics to for second-order optimization. So how can a circuit capture some information about the curvature of the loss landscape instead of only the slope of the loss landscape in the parameter space? Also, how can we train hybrid circuits with analog and digital parts? Because in the short run, I don't think that we will be able to build the fully analog chips. We will still need some digital parts. And also, a question of importance is by the time we can actually get those circuits for real, how do we accelerate circuit simulation? Because we need to produce proof of concepts that on-chip learning is possible. So all of this research is about producing proof of concepts for analog in situ learning. So by the time we get this hardware for real, and we can actually test those algorithms at scale, we need to prove them at scale first with some proof of concept. So we need to have efficient circuit simulation techniques. And finally, other research questions, namely how can we come up with hardware-friendly alternatives to backpropagation? For example, how can we execute the forward pass and backward pass simultaneously to reduce the latency of the chip, et cetera, et cetera. So there are many interesting research questions, and actually, I'm missing some slides here. I'm not sure I gave the correct version, but I can quickly mention a few things without slides. So just to give a personal take on neuromorphic computing. Note that I haven't pronounced brain so far, the word brain so far in my presentation. And because I think that biological inspiration must remain a means rather than an end by itself. And I think there should be less hype about brain inspiration and more painstaking engineering to reduce the energy consumption of inference and learning at scale. And I question the relevance of biological inspiration at the computational level for energy efficient AI. Is it still relevant? I don't have the answer to this, but I'm just raising the question, and I'm happy to have anyone's take in the audience. while it's obvious, I think that we can gain a lot from biological inspiration at the behavioral level. For example, our most efficient reinforcement learning techniques I don't think they closely match the intelligence of even very simple animals. So there's definitely some gains here, but at the computational level, namely for inference and learning, credit assignment, namely, do we still need the biological inspiration? This is something that I'm not really convinced about. And I'm also wondering about the relevance of the analog versus digital debate. I think that we need to embrace both and actually co-design both analog circuit and a digital circuit, as IBM Research is currently doing, by the way. And also, just to finish off quickly, here's a list of research topics I would recommend to an incoming PhD student into neuromorphic computing or, say, energy-efficient AI. I think that there's really a need for the development of new theory, namely theoretically grounded inference and learning algorithms that are as close as possible to hardware constraints, with this idea that you want the model to be the physical system itself. I think there's also a pressing need for software engineering to be able to, building tools to efficiently simulate large-scale analog hardware, analog circuitry. Also, again, want to emphasize that while a lot of people have been looking into first-order optimization grounded in circuits, or say biologically plausible first-order optimization, we need to look beyond for second-order optimization. And the reason why it's not so well known, so most second-order optimization techniques are not well known, is because it involves some matrix inversion, which are extremely costly on digital hardware, but can be made really efficient on analog hardware. So I think it deserves some attention. Also, lots of interesting questions around architecture design, namely layer mapping. For example, how do we map attention into analog? That is not so clear. And I'm not aware of most recent work, so it might be that people have come up with interesting things on this, but I think it's still an open question as to how to efficiently map a given impression onto hardware. Also, a lot of device engineering is needed. I think we need to come up with reliable analog materials instead of having highly noisy, nonlinear analog materials for artificial synapses and neurons. Finally, I think we need to come up with principal techniques to co-integrate analog and digital circuitry. And I don't think that we will ever build a fully analog chip in the short run. And finally, I am particularly interested also by memory-aware algorithms, namely I/O algorithms. I don't know if you are familiar with flash attention, but I think this is very, very promising. And so there's nothing, I would say theoretically groundbreaking, but I think it's, really smart engineering to take into account the different memory levels, for instance, here for the flash attention in the GPU. And I think that it's another example of how to take hardware constraints into account at the algorithmic level. And so, thanks a lot for attending. And if you have any question, I'm happy to answer them now.
Thanks a lot, Maxence. Thanks for this interesting talk. I tried to capture and help out a bit with a new slide. I don't know if I got your research topics well. Would you say that's correct? Development of new theory that is close possible to hardware constraints, software engineering for large-scale simulation, not just a focus on first-order optimization, layer mapping into analog hardware, then flash attention. You mentioned flash attention.
Memory-aware algorithms. So what is called I/O algorithms in the literature, as far as I know?
I/O algorithms, yeah.
Mm-hmm. Also, device engineering. But that's about it. Yeah.
So that's okay. Okay. Thanks a lot. Really interesting. I think I would like to start a bit with some clarifications about RAIN, because also it's been in the news quite a bit, and so for anyone who has followed RAIN's website in the past years, it started off with a focus on mixed signal hardware, at least from the website, and equilibrium propagation. Now in your roadmap. And now it says focus on in-memory computing. In your roadmap, it's the other way around. Can you clarify a bit on that? How
Yeah. So I would say that the startup actually started off working on equilibrium propagation, analog computing, and we have realized that the focus should rather be on digital hardware and standard algorithms in the short run. And so right now, so I would say that all of this research revolving around equilibrium propagation and analog hardware has been postponed to later, to after coming up with our first digital chip. So that's why it's reversed now. So we want to focus, at least our engineering efforts should first focus on the design of this digital chip. And then in the longer run, we will, as analog technologies improve, we will eventually, implement learning algorithms like equilibrium propagation or other learning algorithms. Later. Yeah. So that's. I hope it's clearer now.
Yeah, no, absolutely. Thanks for that. There was also a question in the audience about the investment of OpenAI into Rain. Like how does that play into? I think the audience is curious about how that plays into. Does that affect your daily life? Is that is OpenAI or Sam Altman is the official investors or?
So yeah, I can say a little bit about this if you want. So there are two different things. So Sam Altman personally invested in our startup. Like he actually gave $1 million as a seed round. And then we actually recently heard about this 40-ish $1 million investment from OpenAI. And so yeah, just to clarify it up front, this is old stuff, and this actually refers to so-called letter of intents, which are known as LOIs. So LOIs are actually, they are tremendously needed for a startup, to gain credibility. Namely, you have an investor that says, hey, when your technology is available, I will buy this amount of your chips. And so we actually have this letter of intents. However, they are only letter of intents, so they are not binding, meaning that OpenAI is not compelled to buy this amount of our chips when they become available. So that's why there are some people that call this letter of intents letter of nothing. So yeah, I would say there's no. Of course, it's great, to be somehow attached to OpenAI, but on the other hand, it's. So in the short run, we don't gain much from it. It might be later in the future, but right now, immediately, it's not the case right now.
Cool. What would you say is a timeline of like when would people be able to buy such a IP? Is it IP? Is it off-the-shelf hardware that Rain is developing currently? In terms of like the timeline, do you think you could give some more details?
So we are actually able to sell our IP right now. I would say we are currently, discussing with the potential clients that would like to acquire parts of our IP. And so we are still proving our IP right now. There is a precise process for this. But for people that would like to buy our chip, they would have to wait a little bit more. So we are sending our first tape out this year, like in a few months actually. So we should have parts of our chips actually delivered and built by the end of this year. And probably next year we'd be able to assemble the whole chip. So 2025. I would say this is the deadline. Yeah.
Nice.
I'm not mistaken.
Best estimate. I have a question around. Do you know this paper about the hardware lottery? I think it's written by Sarah Hooker, if I remember. Well, it says that basically because we in a parallel universe maybe we would have thought. We would have found out about asynchronous hardware and maybe analog hardware, or it would have basically taken a different shape in our computing landscape if maybe there hadn't been computer games, that forced the development of GPUs and so on. And it says that basically because some decades ago we went on one of this pathway of digital synchronous compute. We put a lot of effort into it, into miniaturization of the process and so on. And so it's hard to shift away from that. But that it doesn't mean that maybe there is some other principle in maybe analog computing or in bio-inspired computing that that could be better. How do you see that? Because I see that Rain, when you talk about this digital IP, it is focused on building on what's currently the most developed. I would say, which is digital architecture. Can you elaborate a bit on taking risks, maybe exploration versus exploitation? That's yeah.
So how do we go? Yeah, okay. So here's how I will illustrate this idea. So there are two extremes. Rain could be focusing solely. So yeah, looking at my hands right now. So Rain could be focusing solely on inference and digital, but then it would make no difference with respect to its competitors, and that actually would be lagging behind competitors which are well ahead of Rain in terms of the development of digital chips and dedicated to inference. At the other end of the spectrum, yes, we could be entirely focused on analog and equilibrium propagation kind of research, single order optimization grounded in circuits and so on. But then of course, that would be risky because we don't really have good enough analog technologies available right now to be able to build a viable product. So taking these two extremes into account, there's an optimum in between, right? So then the discussion is how do we balance things out and how do we balance exploration and exploitation? I would say right now we're doing a good job at this because we have a research team and we embrace research. And so while some people are working on the design of the product, some other are actually working on research. Actually, not a lot of them. So we are not really a lot in the research team right now. We're not actively recruiting for research. But it might be that we recruit more if we can raise a Series B this year, which is in the pipeline. And so, yeah, I would say that the best way to balance this out is to maintain a research activity, and to look more into fundamental analog research. And I don't know if that answers your question.
It does.
Clearly, but
Basically,
also,
you hedge your bet. Mm-hmm.
Also, I would say another way to accommodate this need for look into analog and while leveraging digital is to actually look for the design of this hybrid system. And I think it's a false debate to say we should ditch analog, focus on digital, or vice versa. I think that we should really marry both into the same set of ideas. My vision actually in the short run is that some part of your circuit, so what the circuit would look like, at least the way I see it is, it would be made up of analog and digital parts. It's exactly like IBM is currently doing, actually. If you look into this North Pole architecture, it's made up of digital parts, analog parts. And so the question is really, in the short run, how do we make best use of analog and digital, and how do we use analog without having the advantages of analog being offset by the extra digital circuitry incurred by the use of those analog parts? And so, that's also, a sub-answer to your question.
Nice, thank you. Given that the Rain pivoted away from analog for the moment, at least, and there's also other companies like Mythic AI that try to build analog or mixed signal AI accelerators that try to mix digital and analog IP. Like they also had to pivot away from mixed signal. Why do you think is that? It's like is there? It's just about finding the right way to do it, or I don't know. Are we digging ourselves a hole, or it seems, yeah.
So honestly, I guess it's about the way, the way to do it. I don't have a precise answer to this, and of course, we have to learn from other people's attempts at doing this. And I'm not yeah, I'm not competent on all the parts of analog. Of hardware design to actually answer this question precisely. How should we do differently from other people who attempted to do this? Mixed design. Yeah, I mean it's hard to answer. In a short answer. So yeah.
All good. No, I understand. It was a bit of a broad question, maybe. I'm gonna put some questions from the audience. So, can you clarify if you think the first commercial RAIN chips will be inference only, or does the in-memory acceleration also apply to backward gradient computation?
So no, our first chip So our first chip will not be only about inference, but also about learning. So it will be able to actually do both. Yeah. Oh, thank you for showing the question. I can actually reread it. So yeah, no. Our first chip will normally be able to compute gradients as well. Yeah.
Yeah. And are you okay? You said you're targeting vision models. Okay. Okay. Another bit of an open question. What do you think the next 5 to 10 years of neuromorphic compute looks like?
Well, I think first, I don't know what is meant by neuromorphic compute, so I will perhaps rephrase the question as I don't know, optimized energy efficient chips, or say, yeah. So I think first, what it would look like in the near term, I think it would look like optimized digital hardware. I don't think that we will reinvent the wheel within the next 5 years. I think that we've made. It depends if we consider inference only engines or inference and learning engines. I think that IBM Research is really doing a great job for inference engines, and actually they're starting to prove those approaches at scale. But actually, these are not fully analog chips again, so it's a hybrid of digital and analog chips. So I think that we will have available. So my take is that we will soon have available those inference engines, hybrid analog and digital inference engines commercialized. I would say definitely within 5 years. I'm pretty sure about this. Beyond this, I think that we will keep building upon this hybrid analog digital design towards incorporating more and more analog parts, being able to map new operations beyond convolutions and linear operations into analog hardware. I think that analog technologies will also improve, and I don't think that we will be able to sustain training from scratch in these hybrid architectures, but probably fine-tuning in the short run. Then as analog technologies improve, I think that we will be eventually be able to perform training from scratch on those analog digital architectures. And then, probably in an even longer run, perhaps we would be able to get rid of all of the digital components and, then perform analog end-to-end. But honestly, this is highly speculative, and I have absolutely no idea. And also, I don't think there's a clear idea neither of whether the brain is actually a digital or analog substrate. I don't have a clear idea about this. I remember when I was in Hanover in December 2018, actually the first time I met up with Ben Sellier, there was this guy from an American university who actually did some research to actually understand whether the brain was analog or digital, and the answer wasn't actually clear. It was a little bit of both. So should we even aim at building a fully analog systems? I don't know.
On that, I have a follow-up question here. What do you think about memoristic technology? Like, do you think this is a viable path to do, or?
So it depends a lot. So it's always about trade-offs. It depends on the technologies, the kind of memoristic technology you use, whether you use them for neurons, whether you use them for synapses, whether because for example, when you hear about people mapping pre-trained models onto analog substrates, I mean, you can easily deal with memoristic imperfections, namely if you have weight tuning protocols with closed feedback loop to accurately program pre-computed weights onto your substrates. Also, if you use multiple memory sleeve devices per memory cell, then you are able to mitigate further the imperfections of your devices. So memory store-based implementation soon for neuromorphic chips. So for inference, yes, definitely, I think so. But then, I think the questions would deserve to be broken down into several cases, several pieces. But so yeah, I would say for inference, yes, definitely. For learning, I'm more doubtful about this. No, probably not. So yeah, I guess it's. I already answered this in the previous question.
Given that we're at Open Neuromorphic, what efforts or are there any like open source implementation of models, code, hardware? Like, can people play with your stuff? Do they need to buy a chip first? How does that work?
Are you talking about my own position or that of Rain?
Both, either.
So yeah, I think it's really. Yeah, I think it's fundamental to go open source with regards to at least any software that we develop at Rain, because we want people to look into what we are doing. And for example, I've been helping on the development of a code base that is owned by Ben Solier, which is about those energy-based learning algorithms on analog so simulating equilibrium propagation on analog circuits. And I mean, he actually released this code base recently, and I think it goes in a good direction of having people working on the same on the same problems. Having people helping us optimize this code and be able to simulate larger scale systems and perhaps extend this code base. So I think that it's absolutely crucial to open our code base to outside researchers. So it's so that this field actually moves forwards faster. And also I think it's important that people from different communities work on the same problems. And I think this is one of the problems of the neuromorphic computing communities, that we may not have enough theorists working on neuromorphic computing, or perhaps not enough software engineers or like core computational scientists working on neuromorphic engineering. So I think that open sourcing goes in the direction of this transdisciplinary collaboration. So I think it's really important to open source our work.
Mm-hmm. And is there a GitHub repository for Rain? Is there maybe an implementation of equilibrium propagation somewhere?
There is one actually. If you look into our most recent RIPS paper, actually that was accepted in December. So there is actually the link to a code base, a GitHub code base that is publicly available. So people can use it. Other than that, for the code that pertains to the we haven't yet released the code that we are currently using for the design of our digital chip, but for longer term research, yes, definitely we are releasing our code.
Nice, thank you. Another question from Guillaume. On the theoretical side, ECPROP is more adapted to analog computation. Do you see a similar promising theoretical research direction for hybrid computation?
So I don't know what is meant by hybrid computation, but I suspect analog and digital. And actually, thank you for asking, because I'm actually working on this right now with a student from Mila. So we hope to be writing a paper soon about this. But actually, you can use equilibrium propagation in hybrid system made up of analog parts and digital parts. So what I mean by analog and digital here at the highest level would be, you would account for digital parts with the feed-forward parts of your model, and analog parts as energy-based parts. So if you consider a model that is energy-based by pieces, by blocks, then you can still train it by equilibrium propagation. Thanks for asking.
Nice, thanks a lot. Honestly, this is the busiest talk we've had so far. I think people are quite interested in your research. So maybe we can also, if we can maybe link, we will put some of the links to Maxence's papers and publications maybe underneath the talk, so that the guys can also follow up with it.
Mm-hmm.
Cool. All right. What is, I have one more here about the trade-off between, or maybe can you clarify what is the role of RISC-V in the hardware?
Yeah, exactly. So yeah. So the answer is in is in the question actually. So yeah. So we use RISC-V for anything that we could not natively implement inside the INC core. And so namely this softmax, pooling layer, yeah, exactly, yeah. Softmax, pooling, yeah, this kind of operations, yeah. I don't have much more to say about this, but I know we are licensing the RISC-V from Andes. I don't know if it's relevant here, but actually, yeah, we are building our own custom RISC-V on top of some existing RISC-V. I'm not an expert on this especially, so I cannot talk much about this. And also, I think it's IP sensitive. So
understood. I have last question. Would you also consider your IP relevant for cloud applications? How does it work for like large scale models and like? Can you clarify on that maybe?
So I'm not sure I understood the question. Is your question about, so do we consider the cloud market or?
Yeah.
Or
yes.
Okay. So I think it's still under debate. And also, so yeah, I think to be perfectly objective, I am not sure that there is a clear answer to this within Rain. I think that we consider both because we have clients traction on both these markets. If you ask me about my personal stance about it, I think that we should stick to edge compute because I think it's a market that is not enough explored, and there are lots of competitors on the cloud market, and also I think that we are clearly lagging. I mean, that's my personal view. I think we are still lagging behind people that are optimizing LLMs on digital substrates for cloud. There are many competitors there, and we hear a lot, for example, about Grok, or this kind of startup that is really already well ahead of us for optimizing the inference of LLMs in the cloud. And whereas I think that we are still, at least that's my impression, we still underestimate the importance of the edge market because we are just so much used to the idea that we perform compute on the cloud that people tend to forget about, why would we ever perform inference and learning at the edge? I was recently talking, when I was in San Francisco, to a friend working at Amazon. So his job is actually to sell cloud services, and I was actually asking him about what he thought about this edge market, and he couldn't actually understand why there was such an interest about edge, because for him and probably for a lot of people, it's obvious that you just perform your computation on the cloud. And so I would say in the short run, people clearly might have incentives to consider the cloud market, both on the client and on the startup side. But in the longer run, if we want to build, I think, AIs that are more respectful of ethics, of people's private life and people's privacy, I think that we should. And also, if we want to go for, technologies that are less energy consuming, more ethical as well, I think that we should really go edge. And personally, I think that there's a strong ethical incentive to consider the edge market. I mean, in spite of the incitations to go on the cloud market right now.
Nice. Thanks a lot for that insight. Yeah, we are at the end of this hour. Is there any last, do you want to say something to close this talk? I think we lost him, unfortunately. Let's see if he comes back. Oh, there he is.
Sorry.
Lost you for a second.
So anything that I want to say to close this presentation? So yeah, I would say there are lots of interesting stuff to be done, and in this field, I think that biological inspiration is I think it's overhyped. So I think that people should really focus on, painstaking engineering, doing good science, and not caring about like replicating some part of the human brain, unless of course the focus is on better understanding the brain. But whatever it comes to building energy efficient hardware, I'm not sure about the relevance, but it's a personal take. I'm not engaging Rain's opinion here. I don't think it's relevant to take inspiration from the brain. I think that we know what triggers energy consumption, separation between memory and compute, and the cost of compute. So then, if we can optimize for it, then good, And if you disagree with me, or if you want to discuss with me, you're more than welcome to email me. So you can easily find my email address. So yeah, please don't hesitate to reach out. If you're interested about Rain, want to hear more about Rain, don't hesitate to reach out. And yeah, and if you want to discuss science or potential collaborations, I don't know. You can reach out.
Thanks a lot for these words. I really like your pragmatic approach. I think it makes a lot of sense to me. Yeah, so with that, I think thank you again a lot for this talk, and I hope that there will be another opportunity for a follow-up one, maybe the next time on
why not? Okay. Thanks a lot for the invitation, Gregor, and I hope it lived up to your expectations.
Of course.
Okay.
Have a good night.
Okay, bye-bye.
See ya. Bye-bye.